Welcome and thank you for joining us for this month's SIG webinar. Today we are featuring an ensemble cast of scientists who are utilizing the Mantle convection code aspect to study a wide variety of research problems. Talks will look at terrestrial as well as our own planet, investigating problems on different time and length scales, from polar wander, subduction zone kinematics, mantle heterogeneities, and the East African Rift, and mantle plumes. Each of these science highlights will be approximately 10 minutes in length. We begin today with a short introduction to aspect by Professor Timo Heister from Clemson University. Prior to his current appointment, Timo was a visiting assistant professor in the Department of Mathematics at Texas A&M, where he worked closely with Wolfgang Bangerth in maintaining the deal.ii library. He is one of the key developers of aspect. Due to technical errors, no audio was recorded for the first 4 minutes of this presentation.
Yet. So in order to do that, we decided to try to implement a free surface in aspect so that we could actually put in explicitly the centrifugal forces that arise in a rotating reference frame and allow it to self-consistently come up with the rotational bulge and convect in that ellipsoidal domain and actually update where the rotational bulge is in time. So in order to do that, we have implemented this remeshing scheme. The boundary conditions end up being quite different here because we actually have a free surface. So that's a no-stress boundary condition. And in general, you're going to have a non-zero velocity in the direction of the boundary. And so the boundary will be moving. So in order to keep the mesh regular, we go through a fair amount of work to try to remesh it so that none of the cells get too distorted, and so that we can have it change and move around in time. So the basic scheme, because I suppose this is in a sense a talk about our code, is that we solve the Stokes system, which is sort of the normal aspect setup, and then we have to do some extra work, which is advecting the surface nodes and then remeshing the interior. And then because the mesh is moving, our advection systems need to be updated in order to not sort of double advect those field variables. And then we actually do our Eulerian type of advection. So I would like to try to show an example with this. I know Timo managed to show a video with a plume. Let's see if I can do likewise. So what we have, what I'm trying to show here, can people see that? Is we've got a planet. This is a 2D calculation, so it's doesn't require quite the computational resources that Timo showed. But we have a planet with a light blob in it, and that blob ends up being a moment of inertia deficit. So the rotation axis, that arrow in the middle is the rotation axis. The rotation axis is pointed towards that light blob, and as I click play, you're going to see the blob rise, and it's actually going to deflect the boundary outwards. And as it deflects the boundary outwards, what we're going to see is that the additional moment of inertia of that boundary deflection is actually going to change where the planet wants to be rotating around, and we're going to get a 90-degree shift in the rotation axis. And that the speed of that shift is going to be set by the ellipticity of the planet, which you probably can't see it because it's very slight, but that sets how quickly that change happens. So this is sort of a simple example of the type of things that we're trying to do with these free surfaces. I know that there are many other applications that people are interested in doing with free surfaces, and hopefully people will be able to use it for other things as well. So this is my backup if the video didn't work, but hopefully it did. So that was a very simple example. In reality, we've got a vigorously convecting planet, and it's a much more chaotic system than what I just showed. So we're doing simulations in full convection with a fully convecting planet and tracking how the rotation axis moves. And well, I'm not going to explain this, but I think we're getting some interesting. We're starting to put together an interesting story of what kind of rates and magnitudes of true polar wander we expect as a function of the relevant parameters for our system, the rotation rate, the Rayleigh number, and so on. So there's a long list of things. This is not a long list, but we could expand it sort of arbitrarily, of things that we'd like to continue with in this project. And yeah, so I'd like to, again, thank Timo for having me out here. We've, I think, been doing some pretty cool stuff this week. And I can take questions if people have them, or I can go to the next person.
Looks like Renee has a question.
Hi, Renee. What's up? So yeah, so stability is an issue. There are some ways of addressing stability. You may or may not be aware of Boris Kaus's and Dave May and somebody else. I forget. I'm sorry. 2010 paper on that. So there are ways of stabilizing the free surface, which we have implemented, and so I think in our current sort of setup, it's actually not that expensive compared to the Stokes solve. I think we were
5% in 2D.
We were seeing something like 5%. We haven't really extensively looked at what it's like in 3D. But depending on your problem, you can probably get away with less than a factor of 2 of additional cost. And I don't want to say that it's free, but
we also had a smaller time step. So
yeah.
I mean, there's some cost there certainly,
but hopefully not terrible. Okay.
Great. So if you guys can stop sharing your screen, we'll let Katrina take control. Great. So our next speaker is Katrina Arredondo. She's a graduate student here at UC Davis, and she'll be talking about kinematic subduction zones with nonlinear rheology and aspect.
Hi, you can hear me?
Okay. Yes, we can.
All right, so if you can still hear me, I'm Katrina Arredondo. I'm a PhD candidate at the University of California, Davis, and I'm going to talk about adding subduction zone models to aspect. So the motivation for adding these models into aspect is that our research group wants to stay up to date with the latest code from CIG. Our research group is led by Professor Magdalene Dillon. So far my PhD models have been struggling with sitcom-S. The solvers have not been strong enough. They do eventually get to the solution, but at a very great computational cost. Some of my more complicated models are taking about 2 months to finish, about 30 million years. So I'm hoping, and we're hoping as a whole, that aspect will fulfill its potential and be much more powerful and flexible, and we just be better at solving our different scientific questions. All right, so my task for the last part of my PhD is to move all our sitcom-S models and modifications into aspect. So a couple of things that I need to add into aspect, which other people have also worked on, is for one, the nonlinear solver, nonlinear rheology, also latent heat, which I think Julianne has been already added into aspect. She'll be talking later in this hour. I also need active fields or particles so I can change the density of my model. I also need phase transitions. I need to define my temperature field for my 2 plates. And I also need a weak zone, which can move dynamically with the trench. So here on the bottom, I have my basic model that I have working currently in sitcom-S. I want to move this into aspect identically. So I have two different models. I have kinematic, where I'm pushing the subducting plate at a constant speed. And then I also have my dynamic models, where the plate speeds can react dynamically to different forces in the model and change speeds, and the trench can move and whatnot. I also have different convolutional layering, especially in particular basalt, hitting into eclogite around 100 kilometers, a hardwoodite, which is very buoyant, and then also of course my background pyrolite peridotite. So here's I have my basic sitcom-S model, which I want to move into aspect. So you can see on the left is temperature, on the right is viscosity. So the different lines on the left is red, and on the right is white, are my different compositional fields, or defined here by tracers. Then the horizontal lines are defining all my different phase transitions. Here I have about 8 different phase transitions which are affecting the behavior of this slab. This particular model, the trench is also moving on its own, so you can see that it's moved, well I can't see here, but this particular trench has moved to the right. So when all this complexity, which sitcom-S cannot handle very well, hopefully aspect can do better. So I have added a couple of things from that list into aspect. One is to improve and update the iterative nonlinear solver. The nonlinear solver that was released in aspect 0.3 was very incomplete and flawed. It had some needed work. So I've modified it according to the solver in SecComS, which I'll explain here. So how it works is here, you first start your model, for example, at time step 0. You will begin with an initial temperature field, which you defined inside aspect in your temperature module. And you also have an initial guess of your strain rate, which here I have as 1 e to the negative 15 inverse seconds. You'll use this to calculate initial viscosity fields, and then use the Stokes solver to calculate your velocity fields. You'll then use your new velocity field to recalculate a second invariant of the strain rate, which you will then plug back into the viscosity, and then iterate and resolve the velocity field from your new viscosity fields. So you'll continue to iterate this over and over and over until the difference between the new and old velocity and pressure fields are below a set defined precision, which you define as user. So in SecComS, this precision is very small. I think I have mine as 0.01%. So yeah, that's very important to have that very low. So if you have a time-independent model, you would stop here. You would now have your nonlinear solution of your velocity and pressure fields. But if you have a time-dependent model, you will want to continue into new time steps. So now that you have your velocity and pressure fields, you will now advect your temperature and composition with your new velocity fields. Then take that new temperature field into time step 1. So now you have your new temperature field. You have a new initial guess of the strain rate from your previous time step, which comes from the previous velocity fields. And you go through the same thing over again. So you have your new initial viscosity field, redo Stokes solution, and then just iterate once more over and over and over until you have your precision. Now, because in your time step 1 and beyond, your initial guess will be much closer to your real solution. So your first time step 0, will take much longer than the time steps after that. So for example, in SecComS, some of my more complicated models, time step 0 will take maybe an hour to converge, whereas the time steps after that will take 5 to 10 minutes. So this configuration of a nonlinear solver is identical to the one in SecComS. It's proven to work. So that's what I have so far in my version of Aspect. So I've also done some other tasks to add my subduction zones into Aspect. So for our research group, we use a nonlinear rheology with diffusion and dislocation creep, with a cap of yield stress to control the strength of our plates. So here I have on the bottom our screenshots from ParaView. On the left, I have just a depth-dependent slice of my viscosity. And then on the right, I have just a screenshot of my 2D model of the viscosity. So you can see that I have my subducting plate and kind of ending at that little blue square. It has changed. Sorry, it starts at the left-hand corner of the grid where I have my ridge, and then the temperature or the age of the plate increases all the way up to the trench, which is where the blue box is. So the blue box is where I've trying to debug my weak zone code. It's not working yet. And yeah, that's where I am right now. So I have my nonlinear solver working, but I need some more testing. And then I'm currently working on finishing the nonlinear rheology module, my viscosity module, of Aspect. And then hopefully I can start running some simple subduction models and then really test my nonlinear solver. And that's it. Thank you. So
thank you, Katrina. I think Timo has a question. Timo, you probably can just turn on your mic too.
Yeah, okay. I wanted to know how many, you talked about 1 hour or 5 minutes of nonlinear iterations. How many iterations is that?
Oh, see, in SecComS, the initial iteration had maybe, I can't remember, maybe 7 different iterations. It depends on the model, so I don't remember the exact numbers. And then after that, it will finish in about 2 iterations, so it's much faster.
Okay, good. Thanks.
So thank you very much, Katrina. We'll still, of course, take more questions as we're switching speakers. Our next speaker will be Sarah. Sarah is an NSF postdoctoral research fellow at MIT. Her interests include lithospheric dynamics and GPS with the long-term goal of decreasing geohazard risk by improving our understanding of the Mantle lithosphere system. She'll be discussing how aspect will help her in her studies of the East African rift system. In her talk, Implications of Vertical and Lateral Viscosity Variations of the Mantle lithosphere system in the western branch of the East African rift.
Thank you, Lorraine. Good afternoon.
Great.
Thank you for the opportunity to highlight this research project. I've been working on this with Wolfgang Wengertz and my mentor here at MIT, Brett Hager. So I've been working on the kinematics and large-scale dynamics of the East African rift system for almost 8 years now, and I'm actually thrilled to be applying a 3D modeling technique to the region. I'm using aspect to investigate the implications of vertical and lateral viscosity variations of the Mantle lithosphere system in the western branch of the East African rift. The reason to study such a problem is illustrated by this image in the background. Volcanoes are a physical manifestation of continental rifting. So when we understand the physics of these systems, we can make significant progress towards mitigating hazards like volcanism. The East African rift system is a fantastic natural laboratory for studying continental rifting. It's actively diverging the Nubian plate and the Somalian plate. So this is the Nubian plate over here and the Somalian plate over here. Let's see. Current extension rates are very small. They are less than 1 millimeter per year in the south and 5 to 6 millimeters per year in the north. An advantage to studying the East African rift system is that it's actually isolated from major subduction zones. There are 3 dominant forces driving plate tectonics. They're from slab pull, internal lithospheric buoyancy forces, and mantle tractions. So in East Africa, we simply have mantle tractions balanced by lithospheric buoyancy. Now, I am particularly interested in the western branch of the East African rift system. I've highlighted here in this image one branch. So there's many branches of the whole system, and this one it's about here. There's new GPS data that's shown in red. We're observing a signal that's unlike anything we expected to see. I'm showing you here 3 different colors of vectors. The red vectors are the GPS data. The white vectors are what we expect if this was simple plate tectonics occurring here. So if we had rigid plates. And then I've done some dynamic modeling just using 2-dimensional models. And those allow me to test the role of lithospheric buoyancy forces and potentially the role of mantle tractions as well. But here I'm showing you the green vectors are from the role of lithospheric buoyancy forces. And that is the major force that's driving the entire rift system as a whole. It turns out that mantle tractions are actually playing a very small role for the entire rift system. But that's for the system as a whole. We don't know what's happening within these individual branches. The green vectors here are assuming a specific effective viscosity model for the whole lithosphere. It's vertically averaged, and I'm showing you that in the background. It's very coarse resolution, so there's certainly a need now to get better constraints on viscosity, both vertically and laterally, so we can determine what is actually driving these long rift motions within the western branch. So what I've done so far in collaboration with Wolfgang is to build a 3D numerical model of this area. The figure on the top it has a black box, and that's illustrating the region I just showed you. And then it actually has topography built into the surface. So I've shown you the image of topography to this in the bottom image as well. Of course, we're solving the momentum, Stokes momentum equations, and it's the Boussinesq approximation. So with this particular model, it was important to me to build in Earth's curvature. We're modeling an area that crosses the equator, and one of the things I want to test is if curvature of the Earth actually has a role in the dynamics in this region. So that is one nice part of this program that we could build that in there and actually have that as a possibility to test. So these initial models, what I've done is I've put in a variable lithospheric thickness. So we modified aspects so that I can put in whatever lithospheric thickness I choose to test. And I make the base of that lithosphere a reasonable isotherm. So here it's 1,673 Kelvin. And that's a reasonable approximation for the base of a thermal mechanical lithosphere. In these initial tests, I made the viscosity of the lithosphere just high viscosity, so it's a viscous lid. And then we've imposed a Newman boundary condition. And then for the viscosity of the mantle, I'm using a diffusion creep flow law. The figure to the top is showing you the temperature distribution. In this initial case, I input a lithospheric thickness model that's very coarse. So I do want to preempt the solution, just so you're aware, this is a very coarse lithospheric thickness model. It does not actually reflect the true topography at the base of the lithosphere in this region. The figure to the bottom is the viscosity. And you'll see there's a kink in this figure. It's not really kinked. That is an artifact of the visualization code visit. But I do want to point out in this figure to the bottom that here we have, so the high viscosity lithosphere, this is what we expect. And then we're also capturing the lower viscosity asthenospheric region. So we should see viscosity behaving this way, in that it gets it's lower viscosity here, and then it increases with depth because pressure becomes the major factor in this viscosity equation for diffusion creep. Okay. This is the initial result. I show you the viscosity as well as the velocities. We are getting upwelling and downwelling where we expect. So we should be seeing upwelling in this region over here. This is actually where we have the thinnest lithosphere, and then we should get downwelling over here where our lithosphere is thicker. I also want to point out that we are getting relatively higher velocities in the lower viscosity region in the mantle, which we should be seeing that. And then at the surface, we also would expect that the surface velocities are very small here. So everything at this point is functioning the way we want it to. And we're at the point now where I can test different lithospheric thickness models, and these are going to be based on actual data from the Western Branch. We have observations from volcanic lavas in the region that give us depths of melting. Those melting depths can also be used to impose realistic variations in viscosity, lateral and vertical. So, testing additional lithospheric thickness models is some of the future work. I'm also interested in building in dislocation creep and working on the boundary between the lithosphere and mantle and making that more realistic and testing the parameter space for viscosity. And then in the end, I'm very interested in figuring out what viscosity structure and lithospheric structure do we actually need to explain the GPS data at the surface. Maybe it's not for mantle flow, maybe it is, but using aspect is a way that I can explore that possibility. So I will take questions now.
Thank you, Julianne. We have one question coming in. Oops. Here we go.
Okay, how many? This is a instantaneous flow model, so it's only one time step.
How do you evaluate the effect of mantle traction?
We've built in the ability to output surface velocities. So this is part of the future testing, but I will be scoring the output at the surface with surface velocities. Sorry, actual observations of surface velocities. You're welcome.
Well, okay, I don't see anybody else typing right now. Thank you very much, Sarah, for sharing with us your research on the East African Rift. Our next speaker will be Julianne Danberg. Julianne is a graduate student at GFC Potsdam. As mentioned before, Julianne will be organizing an aspect tutorial at Geomod in Potsdam this fall. That's September the 4th. So if there are people who are going to that meeting or interested in the tutorial, they should go to the Geomod website. Today, Julianne is talking about her work on geodynamic modeling of eclogite-bearing mantle plumes using aspect.
Okay, hello. Can you hear me?
Yes.
Okay, fine. So I will talk a bit about my models of eclogite-bearing mantle plumes that I made using aspect. And for those of you who might not be familiar with the concept of mantle plumes consist of hot material rising from the core mantle boundary, and when this hot material gets close to the surface, then a fraction of the material melts, and this causes magmatism and huge volcanic eruptions at the surface, and they can possibly even lead to mass extinction events. So on the right side here, you see a classical model of such a mantle plume with this large head and the thin tail. And while these classical models can explain the observations in a first order approach, there are some recent observations that do not quite fit these classical models, and that's why I model mantle plumes. So here in this figure, you see an overview of my models. So first I use 3D models. So you see there the mantle plume just spreading below the lithosphere. You see an isosurface of the plume excess temperature, and above you see the surface uplift calculated with a post-processor of aspect. So you see that as the plume spreads below the lithosphere, it causes a surface uplift of about 2 kilometers. And as there are some effects of mantle plumes that can only be seen in 3D models, I would also like to show you the mesh that I used. So it's actually quite important that aspect has this adaptive mesh refinement, because for plumes, the material properties can be quite different in different regions of the model. So for instance, in the plume head, I would expect a low viscosity, but then the lithosphere above will have several orders of magnitude higher viscosity. So this would be a region where I would need a really fine mesh, but then there are some regions in the lower mantle where I have low velocities and also maybe not so much changes in the material properties that I can get away with a coarse mesh. So this is one point, like one feature of aspect that I really like when modeling mantle plumes. And then another feature that I include in my models is the effect of latent heat release when material crosses a phase transition. So yes, that's already in aspect, and what you see here is a basic benchmark. So the material flows in from the top with a constant temperature and a constant velocity, and when this material crosses the phase transition, then the temperature gets higher. So the increase in temperature is because of the latent heat release, and this release of latent heat is dependent on the Clapeyron slope of the phase transition and also on the density change. So let's look how this effect would be in a mantle plume. So what you see here is the temperature of a rising mantle plume. And you see there are, like for plumes that have the same composition as the mantle, so parasitic composition, you have two important phase transitions in the mantle. So the transition from the lower mantle to the transition zone, where you have an endothermic phase change with a Clapeyron slope that is negative. So when the plume rises and crosses the phase transition, it gets a higher temperature. And then above there is the phase transition between the transition zone and the upper mantle. And here the plume temperature decreases when it crosses the phase transition because of the positive Clapeyron slope. And then there's another feature that I look at, which is even more important, and this is the composition of mantle plumes. So the classical models all look at thermal mantle plumes. That means plumes that have the same composition as the average mantle. But geochemical data suggest that plumes might actually have a different composition than the rest of the mantle, and this would be eclogite. That means the composition of oceanic crust. And on the left figure here you see how we imagine that this eclogite gets in the mantle plume. So if we have an oceanic slab that is subducted, it reaches the core mantle boundary, and there the material can accumulate and it can heat up again. At some point, a plume may entrain a fraction of this oceanic crust as eclogitic material, and then it can rise again with the mantle plume. And on the right side, you see how one important material property, that is the density, will change if we have this eclogite in the plume. So you see the density contrast between this eclogite and the background mantle material, peridotite. So on the lower mantle, eclogite has a higher density than just on top, like just at the border to the transition zone. The eclogite has a lower density than peridotite, and then in the transition zone and upper mantle, the density of eclogite increases again with a peak between 300 and 400 kilometers depth. So that means in a large part of the mantle, a plume that contains a fraction of this eclogite will be denser than this thermal plume, and so it will have a lower buoyancy. And now let's look at one of my models where all these effects are combined. So I have a 3D model of a thermochemical plume with 15% of this eclogite in the plume. And you see a moving plate on top, so this can only be done in a 3D model. So the plate moves from the left to the right. And on the left part of the model, again, you see this density contrast between the two materials. And you see that the plume can rise until a certain depth, and then it forms a kind of deep part of the plume head where material cannot rise further to the surface. And this is just in a region where this eclogite has such a high density that the buoyancy of the plume decreases to 0 or negative buoyancy, and so the material is stuck there and cannot rise. And so there forms this deep part of the plume head, and only a part of the material that has a higher temperature or less eclogite can rise to the base of the lithosphere. And this kind of two-layered plume head forms. And the upper part also gets dragged along more with the moving plate. And also the effects of latent heat also stabilize this deep part of the plume head because it is just above 410 kilometers depth. So if the material would go down again, then it would heat up because of this exothermic phase change. And so that actually tends to stabilize the deep part of the plume head. Now we can also look at this model from the top. So now the plate motion goes also from left to right, and we see that the plume head also gets dragged along with the plate, and then some elongated structures form in the direction of the plate motion. And this actually happens because of small-scale instabilities in the lithosphere. So Now, after I have explained all the different features, I also want to show an animation of this model. So the plume rises from the core mantle boundary, and then at some point it reaches the upper mantle and forms this deep part of the plume head and also the shallow part, and gets dragged along with the moving blade, forming elongated structures. So we have seen that this model includes some quite complex features of the plume, and well, there are some features of aspect that I needed to get all these complex structures in the plume head. So the first thing is I needed the adaptive mesh refinement to get such a high resolution that I could actually resolve these features. So in the background here you see the resolution that I used. And then I needed to include all the complex material properties like the latent heat or the effect of the different composition. And another feature that I also really liked an aspect is that you can so easily switch between the 2D and the 3D models. So you can test a model configuration in 2D, and then if it works, you can run the real model in 3D. And what I plan for the future is I would like to see how this plume interacts with the lithosphere and if it can erode a part of the lithosphere. So for that, I would have to include maltransport. That means I have to implement some kind of formulation of Mackenzie equations. I also would like to have higher viscosity contrasts, and for that I need to go to a higher resolution. And I would like to improve the prediction of the surface topography. So what would be perfect just to use the free surface that Ian mentioned earlier. So that was it from me, and thank you for your attention.
Thank you, Julianne. We have a question, I believe, from Katrina. Katrina, you can also use your mic as well. While those questions are coming in, again, let me remind people of the upcoming webinars, tutorials that are going to be offered. That is, the first one will be offered at CGU in 2014 in Banff. That's this coming May. There'll be a tutorial at CIDR, that's in Santa Barbara in July. There'll be one in Tokyo at ELSI prior to the SETI meeting in July as well. And then there'll be the tutorial during Geomon in Potsdam in September. So Katrina has a question.
Yeah, okay, so this latent heat code already is an aspect. So if you get the most recent developer version, you should already see the figure that I showed in the manual. So this, like you can see this benchmark case, and you can also use this latent heat material model. So it's both already there. And for the phase transitions, I think in this case you would have to implement your own, like the depth of the phase transitions. You would have to implement that like in this material model. It's just like a basic material model for latent heat effects, but you would have to define the depth and the like density changes of the phase transition.
And Timo is indicating that this will be in the next release, coming soon. Again, if you want to be notified of upcoming releases and just be in on development activities and discussions within the community on Aspect, please remember to sign up for our mailing list. You can go to our website at geodynamics.org. There are two lists, Aspect-Devel and SIG-MC. I don't see any more questions coming in, but I'd like to thank all of our speakers today. We had some extraordinary efforts today across many time zones. Thanks, Timo, Ian, Katrina, Susan, and Julianne for sharing your time and your ongoing research. Our next webinar will be at a different week of the month. It'll actually be on May 15th at 2 p.m. and it will feature the Geodynamo team. The Geodynamo team will be talking to us about the ongoing international Geodynamo benchmarking exercise they're running. Hopefully they'll give us a sneak peek on how those performance and accuracy benchmarks are going and what they have done to organize their community to establish these benchmarks. Great. Again, thank you, everybody, and thanks once again to our speakers.